This video is to illustrate how to do complex number calculations on a TI-83 or 84 family of calculators. Now, if you happen to have a TI-89 model, the calculations will be similar, although things are actually simpler on that type of model because of the way that the angle mode works, the degree and radian mode, and I'll mention that later on. But otherwise, things will be generally similar. So to begin with, it's very important if we're going to work with complex numbers that we actually be in a complex number mode. So for example, if I'm in the normal default mode, which is the real mode, as you notice up here, and you may or may not have that displayed depending on which model you have. But if I'm in that real mode, and for example, I want to take the square root of -1, and remember that I have to use this negation symbol to do -1, not a minus sign. Those two are not interchangeable in this calculator. Then notice that it gives me an error. It says I have a non-real answer. And so that's simply not going to work. However, if I want to work with that, of course we know that that should be j, the square root of -1. So we need to go into modes, and we'll go down here to this line here and select either the rectangular mode or the polar mode. Now these modes basically are the way in which your answers will be displayed. They are not related to how you enter your answers or enter your arguments on the calculator. The only effect rather of this is how the numbers are going to be displayed when they're calculated for you. So I'm going to go in rectangular mode right now. I have to press enter to have that take effect. Also, it is if you're in radian mode, polar mode, then the angle mode will matter, whether you're in radians or degrees, and I'll talk about that more in a little bit. Okay, another issue is whether or not you're using math print. Depending on your calculator model, you may or may not have this option. If possible, I think it's probably better to be in the math print mode. It's a little bit easier to read than the classic mode. But if you have an older calculator, that would, I think, be equivalent to the classic mode. Okay, so now having entered those things, I can push clear or second quit, either one. Clear is probably faster. And now if I pull out that last entry that I made by pushing this key here and just enter it again, now I get I, which is the proper result. Notice they use I rather than j because they're using the mathematician and physicist convention for the square root of -1. But in circuit problems, we generally use j as that number. Also, for example, you may notice now that you could take the logarithm, let's say take the logarithm of -2. Well, you know mathematically you can't take the logarithm of negative numbers and get a real number. It's undefined. However, in the complex number system, you can do that. And here's the result as a complex number. So now we're able to do a variety of operations, and you can do also sines and cosine. You can do trigonometric functions with complex arguments. You can do various things that you couldn't do with real numbers, and those will all be supported here in general. Okay, so let's show now how to do some calculations with numbers in rectangular mode. So if I want to enter a complex number in the rectangular mode, I can simply type, for example, say if I want to enter 3 plus 2i, I would just go 3 plus 2, and then the I is found here as second plus the decimal point. So you notice the little I there. And that's something you probably want to remember where that is. Okay, and we press enter, and now that just displays that in rectangular form. So then we can do whatever we want with that. We could take, for example, the square root of that answer. So I can use the answer function there, and it would give us the square root of 3 plus 2i, which is this complex number here. And of course, if I want fewer digits to make that easier to read, I could always go into modes and select the desired number of digits, for example, in the type of notation that I want to use. Okay, now, so you sometimes want to be able to convert rectangular numbers to polar form. So how can we do that? Well, let's go up here and select that argument. That's another way of selecting it, is just enter it. one way to do that would be to use some functions on the math menu. So if we go into the math menu, notice that there's a whole heading here for complex numbers. So if we go there, for example, there are various functions that you can take the complex conjugate of a complex number. You can take the real part, which of course is going to be a real number. You can take the imaginary part of a complex number, which is also a real number. Remember that the imaginary part does not contain the j. You can take the angle, which is going to be the angular argument in the polar form. You can take what they call absolute value here, but it's in complex numbers, we normally call that the magnitude of the complex number. And you can also convert either to rectangular form or to polar form. So since right now I want to convert to that, I'll just go down there to number 7, or I could, I guess, just type 7 there. And I'll enter that. And now when I press enter, that puts it into polar form. So here's the magnitude, the 3.6055, etc. And that angle now, well, what unit is that in? Notice that we have a number multiplying I, and again, you could adjust the number of digits displayed if you wish to do that. So what is the format of this? Well, because I'm in degree mode, that's going to be in degrees. So that's 33.7 degrees approximately. Now it's very important to know whether you're in degree or radian mode. And again, that's something that you would set here. So for example, if I wanted to go into radian mode, I could enter there and clear. And now if I were to take that last entry again and just enter that again, now you notice I'm getting 0.588 radians, which is the equivalent of 33.7 degrees in that form. So again, it matters very much for polar form what angle mode you have set. And it's a common mistake is to not remember to think that that's in degrees, for example, now when it's a radians or vice versa. So you want to make sure you know how to correctly interpret the argument here. And remember, this is e to the I theta, so this is an angle either in radians or degrees. Okay, now that's one way to convert, but there's actually another way, which is perhaps simpler. And I could just go up, for example, and take that 3 plus 2i that I used up here. And if I want to display that in polar form, I don't necessarily have to use those functions on the math menu. An easier way is just really to set the mode of the calculator to what I want before I press enter. So I can come down here and set it to the polar mode and just press enter to register that and then escape. And now if I press enter, and I didn't have to do that, say, before I put this in, notice, now it did move the cursor back, which might be a little inconvenient sometimes, but you can always, replace that if you need to. I can just press enter, and notice now I also get the number in polar form. Generally, that's probably going to be the easiest way to convert between rectangular and polar forms, is simply to change the mode before you press answer. And if you know in advance what type of format you want for your answer, you can simply select that ahead of time and then avoid having to make any last-minute changes. Okay, so that's how to convert to polar form. So let's talk about doing some arithmetic. So let's suppose we wanted to add two numbers in rectangular form. Well, to be honest, we can often do that in our head. Certainly if they're integers, we can. But if they're decimal numbers or something, we might want to use a calculator for that. So let's suppose that I had, I don't know, I'll put parentheses around it, 6.231 minus I times 5.379 or something like that. Something that's a little less trivial than just integers. And now I want to add another complex number to that. And let's just make this one a little bit simpler. So we'll just, well, actually, let's put some decimals. 8.23 plus I 1.59, say. Okay, so now if I press enter, that will simply display the answer. Now notice it's giving it to me directly in polar form. So in general, I can get whatever form I want. If I wanted that instead in rectangular form, I can just go back here and change back to the rectangular form. And now I could just bring back that answer and display that, and now that's being displayed in the rectangular form. And now you could check that the 6.231 is added to 8.23 to give me the 14.461, and the negative 5.379 is being added to this portion here, which I'd have to go up to read that and scroll over. Well, actually, I'd have to probably bring that down again to see it. It's a little bit difficult to see here. I could enter that down here and then scroll over. So, oh, I guess that was scroll over. Anyway, those numbers you can see added up to this value. So generally, addition is very straightforward. And really, while I put parentheses on there, and it's oftentimes is a good idea to have parentheses around a complex number, for addition, it doesn't really matter. So we're always bound by the normal order of operations on a calculator. So you know that, for example, the first thing in that order of operations is negation, in other words, applying a minus sign, then exponentiation, raising things to a power, including square roots, then multiplication, division, addition, and subtraction in that order are carried out, and then also moving left to right within any particular operation. So that's the standard rules that you learned in algebra. It's no different on a calculator or generally in computer math. But we can, of course, change that order by putting in parentheses. So you see here, these parentheses really did nothing, and I could have just omitted them, and I would have gotten the same answer. So for example, if I come back here and just delete that parenthesis, and then go over here and delete that parenthesis, go over here and delete that one, go over here and delete that one, and press enter, I'm going to get the exact same number because, again, there didn't change the order of operations doing that. Now, an exception would be, of course, if I'm subtracting, because when I subtract, let's suppose I want to, I'll put the first one in parentheses, although that's really not necessary at all, but I'll put it in parentheses anyway. So 2 plus 3i, say. And now I want to subtract, so I use the subtraction sign, not the negation sign, but the subtraction operator. And let's say I want to go 1 minus 2i, say. Oops, I made the wrong thing there. So I meant to go 2i. Okay, so now we really do need these parentheses if we're trying to subtract that entire complex number by order of operations. If I didn't have any parentheses, I would just be subtracting the 1, and then I would be subtracting 2i, rather than in this case I'm actually adding 2i because of the parentheses. This negative sign is going to multiply that one. So the result here would not be the same, obviously, if I omitted those parentheses. And just go back here and just demonstrate that by deleting those. Again, the first set doesn't really matter, but if I delete these, and as you see, I'll get a different answer for the imaginary part, because now it's not subtracting the entire imaginary number, it's just subtracting the first term. So the moral of the story here is, generally speaking, you want to put parentheses around your complex numbers because you want to operate with it as a unit. And that's true whether you're adding, subtracting, multiplying, or dividing. Again, the adding doesn't really matter, but subtracting, multiplying, and dividing does, or exponentiation, for example, would. Or taking, say, square roots, for example. Of course, inside a square root sign, if you do it that way, then it wouldn't be necessary because that's already in the sign. So it depends on, again, what type of math notation you're using on your calculator. If you need to use parentheses for the argument of an exponential, for example, then you would have to put that in. If you're using this math mode where, for example, I can just go exponential of 1 plus 2i, 1 plus 2i, for example, there I don't need parentheses because it's all part of the exponent, and that will work properly as it is. But if you're putting, if you generally have to have arguments, parentheses around your arguments, then you would need to have that around the entire argument, not around one part of it. Okay, so let's just do examples of multiplying and dividing in a rectangular form. So for example, let's say I have 8 plus I2, and of course it doesn't matter whether I put the I before or after the other number because, of course, multiplication, as you know, is commutative. It doesn't matter the order of the numbers there. Say I want to multiply that by 7 minus, say, I3. Now, you may say, oh, wait a minute. If I'm going to multiply, I should put these numbers into polar form. Well, if you're doing it by hand, that would probably be a good idea. But on a calculator, when you're using the complex number features, that doesn't matter at all. And so there's no reason to convert that. I'll just set up the result to be in the form that I want. In this case, if I want it in a rectangular form, well, I'm in rectangular mode, so it'll come out that way. And so that will just do multiplication. Now, of course, if you're doing it by hand, you'd have to take 8 times 7, which would be 56, and then you'd have negative I squared 6, and I squared is negative 1, so that'd be plus 6. So 56 plus 6 would indeed give you 62, and then you'd say, okay, I've got 14i here, and then I've got on the outer terms negative 24, and that would give you the negative 10. So you can verify that that's matches, but of course the calculator does it much faster, and generally won't make any mistakes as long as you put the answers in, or sorry, put the arguments in correctly. And I could have used implicit multiplication there as well, but I just put a multiplier sign. Okay, and then we could perhaps do the same thing and divide those two numbers. Let's just take that and just edit that to be division instead. And now it's very important using division, again, to have the parentheses, as it was in multiplication. Again, if I omitted those parentheses, I would have multiplied this number times 7 and added the result to negative I3. That would, of course, not be at all the same number as when I do the entire number. So again, your complex number has to be completely within the parentheses for most of these operations to work, probably with the exception of addition. Okay, so when I divide, then there I have the answer. And remember, if you wanted to do that by hand, it would be a little bit involved. You would have had to multiply both the top and the bottom by the complex conjugate of the 7 minus I3, which, as you remember, that would be 7 plus I3. And then you would multiply out the bottom, which would give you a rational number, and that would basically separate the real and imaginary parts. And then you'd have to do the math on both those parts to get this. But the calculator does everything in one step and does it very quickly. So this is a very convenient way to do these types of calculations. And also, as I said, we can do square roots, we can do powers. So for example, I could take 5 minus, say, 2i, and raise that to, say, a power of 5, for example, and just press enter, and it will immediately give me the answer. And remember that if you were going to do that by hand, you'd probably have to put that into polar form, and then that would basically raise the magnitude to that power, and then the angle would be multiplied by 5 since it's e to the I theta. But we didn't have to do any of that, and it just did it for us automatically. Or of course we could have multiplied this out also, but multiplying that out 5 times would be a rather tedious thing to do by hand. So this does it very quickly and accurately. Okay, so that's the math entering numbers in rectangular form. But what if we want to put our numbers in polar form? Well, that turns out to be where some of the tricky things are. And this is going to depend, again, exactly what model you have. And even within a model, it may depend on which software update you have. So I'm going to try to show you what you can and cannot do here. But again, it will be sometimes trial and error to find out what your actual calculator is able to do or is not able to do. But I'm going to show you a trick that will work hopefully on all of these models and will make it relatively easy. So generally when we're putting numbers in polar form, we might want to put, for example, 5, and then we might write it as an exponent, so we'd have e, and then we could put I, and let's say 0.5. And that would be an angle, and I'm in radian mode, so you'd expect that to be interpreted in radians. And indeed it is. And now it's going to display here actually in rectangular form because I chose that rectangular mode. If I wanted to display in polar form, I could go into polar mode here and select that. And then I could go back and just pull back that answer and enter it, and then it will display it the same way I entered it because it was in polar mode. So everything seems fine now, and generally it will be as long as you're in radian mode. The problem here is that very often in engineering problems, we really want to work in degrees. So you'll notice that Circuit Tutor, for example, always asks for your angles to be entered in polar form in degrees. Most engineering textbooks use degrees in all their problems, or most of the problems certainly. And it's just very conventional among engineers to use degrees as the measure of angle, more commonly than using radians. Therefore, we'd really like to be able to work in degrees as a matter of convenience. Well, unfortunately, on this model calculator, that's rather tricky. So you might think, well, one way of doing it, and I'll show you that this may or may not work, would be to go 5. Let's suppose I wanted to put an angle of 45 degrees. So I could go 5E, and then I have the I, and you'd say, okay, 45 degrees. And what happens? Well, that's not showing 45 degrees, is it? Well, it's showing radians. But basically, that's not what you should actually be getting in this case. So to illustrate that maybe a little bit better, let's put that in rectangular form. And you may know that 5 angle 45 degrees would have equal real and imaginary parts. It would be the square root of 2 over 2 times 5. And clearly these are different. So that is not what we expected to get at all. And that's a little bit surprising. So what happens here is that this is actually interpreting this number as being in radians. So this always has to be in radians on this model of TI 83 or 84. Anything within those families, the argument always has to be in radians. Well, as I said, we may want to use degrees, so what do we do then? Well, one would think we could convert that. So we could go, for example, 5E, and then have the I, and we could say, all right, I'm going to be clever. I'm going to write pi, now divided by 180 times 45. So what I'm doing there is I'm taking 45 degrees, and then I'm multiplying it by pi radians divided by 180 degrees. Because remember, pi radians is equivalent to 180 degrees. So I could enter that, and that should be then 5 times e to the I 45 degrees, but converted to radians now. Okay, so the problem is here, well, I'm sorry, it's not a problem. That did work as long as I'm in the radian mode. But unfortunately, however, suppose I wanted to have my answer displayed in degrees. So I could go into the mode and go into degrees. Sorry, the wrong, oops, there we go. So let's put it in degree mode and try that. So now I'm going to take the same argument there and enter that again now when I'm in degree mode. And you see now I'm getting an error. Now, whether or not I get an error actually depends on which software update you have, apparently. If you have a very recent calculator, you're going to get this error when you try to do that. If you have an older calculator, you're actually lucky in the sense that you can enter that and it would have actually worked correctly. But on my calculator or on this emulator, it does not work correctly. So what are we going to do then? That makes it almost impossible to enter numbers in degrees in polar mode. So here's a trick I'm going to show you that allows you to do this regardless of which calculator model you have. And also it'll be more convenient than doing this anyway, even if you have a calculator that will accept this in radian mode. Because again, you don't really want to be in radian mode because then your answers are always going to come out in radians, and you probably want them in degrees, and you'd have to be then converting it constantly, which would be quite annoying. So let's show a trick that we can do. So what I'm going to do is I'm going to define a variable here. So I'm going to say e raised to the power I times, oh, I made a mistake there. Let's go back. Well, I'm just going to clear that and try again. So e to the I times pi divided by 180. And now here's the trick. If I just try to enter this when I'm in degree mode, I'm going to get that error that I just saw. So what I'm going to do is I'm going to go and temporarily put my mode back into radians. And when you first define this, you have to be in the radian mode. Otherwise, it's just going to give you an error. So if you get the error, then that'll be a reminder you've got to be in the radian mode. It won't let you do this when you're in degree mode. So now that I'm in radian mode, I'm going to do that. And I'm also going to then basically take this number, and now I'm going to store it in a variable. So I'm going to go store, and then I'm going to use variable e. And that just helps remember it's kind of like the Neperian e, except it's different. It's a capital letter here now. So by doing that, basically that's going to store that value. And now to test that that actually works, what I can do is I can take e, and I'm going to raise that to, say, 45. And think about what I'm doing. When I raise this number to 45, that basically means I'm going to have to multiply the exponents. If you think about the properties of exponents, if you have, say, e to the a, and then raise that to the b, it's going to give you e to the a times b. So I'm going to be multiplying the 45 times this. Okay. So now, what do we get? Well, we think about 1 e to the angle 45 degrees. If we think about the Argand diagram and just the values of cosine and sine, that should give us the square root of 2 over 2 for both the real and imaginary parts. And indeed, 0.707, that is the square root of 2 over, which is, remember, about 1.414 divided by 2. So that tells us that this is working correctly. And now, even though I'm in radian mode, it works, but I can also then go back to degree mode. And the trick is that this will still work even when I'm in degree mode, even though it didn't work in, well, it didn't work if I did it directly in degree mode. So I can take that same entry, and now it still gives me the same result. But if I had tried to enter it as the full expression, this would not have worked in degree mode. Okay, it would have only worked in radian mode. So now I'm allowed to be in degree mode, so I get my answers in degrees. So for example, if I go back and let's go back into the polar mode. I can take that same entry, and now it displays it in polar mode. And because I'm in degrees, it will show that angle being in degrees now. And so now I have a way of easily entering polar form numbers and having them be correctly interpreted with the arguments in degrees. So I have to remember that I'm going to use that e. So for example, if I want to enter 2 angle 30 degrees, I would go 2. And I could put a multiplication sign, but this calculator allows implicit multiplication, so I'll just use that and write 2e. And then remember that I have to raise it to a power. If I forget to raise it to a power, I'm going to get a very wrong answer, and there won't be any indication that I'm doing it wrong. So that's something you just have to remember if you're going to use this trick. And there's other variations you can find of this trick if you look online, but I like this particular version because it's really, I think, the simplest way of doing things. So again, that's going to show the same format as what we entered. And again, the problem is if you try to do this some other way, this generally will not work. And it's also much easier than having to, even if your calculator will accept the little e to the I pi divided by 180 times 30, then you'd have to enter that every time. And this bypasses the need to do that and just makes it quicker and easier to enter polar form numbers. So I would recommend you use this trick. The only caveat, of course, is you always have to have that variable defined before you start using it. And if your calculator is cleared, for example, at the beginning of an exam or something like that, then you would have to quickly recreate that variable in order to use it. But doesn't take very long, as I just showed you. Okay, so what can we do now? Let's add and subtract some numbers in polar form, for example. Let's suppose I want, I don't know, 4.2 e to the 12 degrees, and then I want to multiply that. And again, multiplication doesn't really matter if I use parentheses or not, because everything's going to be multiplied anyway. Although you might want to use parentheses around these things just to, be a good habit, but it really won't matter here. So I'm just going to write 8.8 e, again, power, say 56 degrees. Okay, and now I press enter. And that will give me the result, which is the magnitudes are being multiplied and the degrees are being added properly. And so that's what we'd expect from multiplication. Now, if I wanted to divide those two things, let's go back up there and grab that and edit it to divide. If I leave it like this, this will not work properly at all. And the problem here is that I'm missing parentheses on the bottom. So if I were to click enter here, I would be dividing this number in polar form only by 8.8 and then multiplying the result by the e to the 56, which is the little e to the I, 56 degrees basically. That's not what you're expecting, and you'd get the wrong behavior of the angle. You'd be basically adding the angle here to this one instead of subtracting it as you should be. And let's just show that. And here you should be getting, of course, you have the 4.2 divided by 8.8, so that looks about right. But when you take the 12, if you were subtracting 56, you'd have a negative angle, but instead it's added those two. So that's the wrong result if I'm trying to divide by that entire polar form number. So what I have to do is to always just remember, basically it's safest to always put parentheses around your complex number. So I'm going to go back and insert a parenthesis here. I'll go to insert mode, put in a parenthesis, and then go to the end and put in the other parenthesis. And now when I divide, it will properly subtract those two degree angles. So now I have the negative 44 that I would have expected. So again, be very careful with parentheses when you're subtracting, for example. Well, actually subtraction isn't so important here, but certainly when you're dividing in polar form, that's very important. Multiplication is kind of optional, but it may be best to just always put them on, and that way you won't forget them when they're really needed. Okay, and again, if I wanted that result to come out in rectangular form, there's no need to do anything else other than just to put the mode into rectangular form. And then I could just do my answer here and enter that, and there's the same number in rectangular form. So rectangular to polar conversions are very easy. We don't have to use square root keys and inverse tangent keys and sines and cosines. And remember, when you use that inverse tangent, you'll often get the wrong angle anyway, because you have to correct then for the proper quadrant that you're in, because the inverse tangent will always return something in the range from negative 90 to plus 90, and that may not be where your complex number is. It may be on the left-hand side of the complex plane. And so doing it that way is much less reliable than using the automatic conversion that's built into the calculator, which will always put you in the right quadrant. So that's a much safer way of doing things. So generally speaking, if you're using complex numbers, except maybe when you're first learning about them, you shouldn't be using the square roots and inverse tangents and so forth that you might see discussed sometimes. Okay, so we learned how to do math now with the polar forms. What if we want to mix rectangular and polar forms? Well, that's really very straightforward. So for example, say I want a number, I don't know, 8.9 e here to the 82 degrees, and I want to add that to some number in rectangular form. Well, how would I do that? Well, it's very simple. I would add, or let's subtract actually. So when I subtract, I have to use the parentheses, so it's good just to remind us of that. So we have maybe 6 minus I3, for example. And again, when I'm subtracting, it's very important to use these parentheses because of the order of operations. Otherwise, I'd be subtracting the 6, but then I would be subtracting I3 instead of actually adding I3 as I do here. So I can just enter that, and that will give me the result. Here I had it set to rectangular mode, so I got it in that mode. If you wanted to have that in polar mode, again, the easiest way is probably just to go in and change it to polar mode. And then we can just take our answer and enter that. Okay, so this is a very simple way of doing these types of things. Again, if you have one of those older models that will allow you to do it, you could use the e to the I pi over 180 times your number every time you enter that. But personally, I find this to be a lot quicker and easier way of doing that. Okay, so as a final and most complicated example, let's go over here. This is a calculation that was being done in one of the videos on AC node solutions on level 3. And so I had this rather complicated expression here I wanted to evaluate for a phasor. So let's just show how you could go about doing that on your calculator. So there's various ways of doing this. I think the easiest way is to start with the right-hand side. And so I'm going to have a negation sign then, and I have a parenthesis, 0.2 plus I times 0.25 again using implicit multiplication between the I and the number, and that's allowed on this calculator model. And then I'm going to multiply that times this. I don't really need parentheses here, but I'll just put them in anyway. So 26.09, and then I'll use that E thing that I've defined, raise that to the power, and then I can just use my negation sign, 48.06 for the angle, which is in degrees, as you notice. And then we'll close parentheses on that. And I'm going to add the other number here. So I'm just kind of doing it in reverse order. So 0.8, angle 30 degrees, so that would be the E, again raised to the power 30. And that's basically the entire numerator. Now, I could do this all in one step, I guess. If I went, I'd have to have put parentheses in back at the beginning to do that. So let's just evaluate this part. And that'll give us that. And then I'll just take my answer and divide here by the negative 0.2. So I'm doing it in two steps just to avoid getting it too complicated. And there's my answer, and indeed that is correct. That's the 38.23 or 24, 0.58 degrees. So in this case, that angle happened to be very small, but that's just the way it worked out. So that's an illustration of how you can do rather complicated expressions. And again, there's not too much need to write down intermediate results. If you want to do that in some cases, you can, but just make sure that you carry out at least, I would say, 4 significant digits, maybe 4 or 5. You certainly don't need to carry out 10. That would just be pointless. But you know, if you want to be accurate to 3 in the end, it would be good to have an extra significant digit in the numbers. Now, very small angles, that probably wouldn't be necessary, but I would go at least out to 1/100 of a degree. It is easy to get round-off error when you're working with complex numbers, so that's something to keep in mind. Carry some extra digits so that you don't have that problem. So hopefully this familiarizes you now with how to do the numbers on your complex calculator, the complex numbers on your calculator, and that would conclude this lesson.